Hi, I'm Lucio Galeati, and I'm a PhD student from the University of Bonn. What I will present here for the One Word Symposium is a joint work with my supervisor, Massimiliano Gubinelli. So what I want to focus on is one of the easiest to formulate, but also one of the most interesting problems in regularization by noise. So specifically, I will consider the following type of additively perturbed ODE, where now I have, for simplicity, already written in the interval form as a Cauchy problem, where I want to understand conditions for the continuous additive perturbation W, such that this equation is well posed, even if the original one without W is not. So before proceeding further, let me just make a quick recap of the theory. So if this Lipschitz existence and uniqueness is known to hold, while if we weaken the regularity on B and only require it to be continuous and bounded, existence is still granted. But there are examples for which uniqueness fails, and actually we have infinitely many solutions starting from the same initial data. If we further weaken the regularity and only ask B to be measurable and bounded, in general, not even existence will be granted. At the same time, it is well known that if W is sampled as a stochastic process, think of a Brownian motion, actually as an SDE with additive noise, this equation is well posed in terms of strong existence and pathwise uniqueness under very mild conditions on B. For instance, it is enough for it to have suitable integrability conditions. And this goes by the name of regularization by noise phenomenon. But what I want to follow here is an alternative approach with respect to the more probabilistic standard one in this field. So to actually completely split the analytic and probabilistic parts of the problem. So to first identify analytical properties of the continuous perturbation W, which ensure well posedness, and only later to find examples of regularizing paths W, in the sense of either stochastic processes whose trajectories satisfy almost surely these analytical properties, or by understanding if generic continuous functions will satisfy them. So in particular, I will consider a given drift B and will try to find conditions on W, which are possibly tailored on this given fixed B, which regularize the ODE. And an early precursor in this direction was the path-by-path uniqueness resolved by Davy in the case of W being the Brownian motion. But what I will follow actually is the approach by Catellier and Gubinelli, who already answered to the first part and part A of the second problem by systematically using the framework of nonlinear Young intervals and nonlinear Young differential equations. So the idea by Catellier and Gubinelli goes as follows. Suppose we have a given solution X to this equation. Assume for now B to be, for instance, continuous and bounded for simplicity. So existence is known to hold, and this is all well defined. Then by the structure of the equation, any solution X actually has to look like W plus a more regular term. And one way to see this is to say, okay, let's define theta to be the difference between the solution and the perturbation. Then theta will now solve a more classical ODE, where now W appears inside the drift. But now the point is that typically when you sample W as suitable stochastic processes like Brownian motion, its realizations will be extremely oscillatory. And one way to see this oscillatory behavior is to understand how many cancellations it can make. In particular, if we define the average field TWB as follows, so basically taking integrals of the drift B along the path W, possibly shifted by an element of RD, then we expect, if there are many cancellations, this new object to be spatially more regular than the original drift B itself. Let me stress this part because it's highly non-trivial, because it's not going to be true for any continuous function W. Here the point is that if I just integrate over time, I can expect a time regularity improvement, but not a spatial one. And instead, truly the point is that these very specific trajectories W are such that you can trade off between space and time regularity in a very non-trivial way. So either way, if you assume that W is such that now this object has higher regularity than B itself, then since X looks like W, you expect the same to happen in that case. And in particular then, this equation for theta, which is a classical ODE, actually admits an alternative formulation as a nonlinear Young differential equation driven by the average field TWB. So let me digress into the abstract nonlinear Young integral framework. So given a field A, which might depend both on time and space, I will define its time increment. I will denote its time increment A of ST as follow. And I will say that A has this kind of joint space-time regularity, C alpha C beta, if its joint space-time increment is controlled by the time increment to some power alpha times the space increment to some power beta. More specifically, I will say that H in C alpha C beta, if we have this control, as well as similar one for the time increments for fixed x and for the space increments for fixed time. And with the first big result by Catellier and Gubinelli is that indeed, if A has this kind of regularity and theta is a gamma order continuous path, then it's possible to define the integral of A along the curve theta as the limit of the Riemann-Stieltjes sum, so as follows. And moreover, actually, now this can be done not only for capital T, but for any small t, and it defines a C alpha order continuous map. So it inherits the time regularity of A. And it's called the nonlinear Young interval because it's a natural extension of the classical one. Particularly if A factorizes as a function f, which only depends on space, and then g, which only depends on time, then actually the nonlinear Young interval corresponds to a more classical Young integral. And so having defined nonlinear Young integration, we can also pass to study nonlinear Young differential equations, namely fixed point theta to the following type of equation. Here, as is typical of the Young regime, I need to impose the time parameter alpha to be greater than 1 alpha. And the solution theory can be developed and goes as follows. So if A has a suitable C alpha C1 regularity, by compactness, existence of solutions holds. If moreover it has one additional degree of regularity, then a uniqueness can be established, and in this case also the YDE admits a flow of diffeomorphisms. Moreover, we have stability estimates, which implies that the solution theta will actually depend continuously and in a Lipschitz way actually on the data of the problem, so the initial data and the drift A. Finally, if A has spatial higher regularity, then the flow associated to the YDE will inherit it. So, okay, the reason I digressed on abstract Young calculus is because, remember, we established that given a solution X to the perturbed equation, the difference between X and the perturbation W now will solve a nonlinear Young differential equation driven by the average field TWB. So indeed, if TWB now has regularity C alpha C2, we can apply the previous theory to deduce existence and uniqueness of solutions. And now the nice feature is that truly this theory only relies on the regularity on TWB and not on B anymore. So remember, I originally assumed B to be continuous just to make all the computations rigorous, but now actually we can drop that assumption. And okay, this is now just a technical lemma to say, okay, if B is distributional, then it's still possible to define the average field TWB at least as a distribution. So it makes sense to talk about it, and we can postulate it to have higher regularity, to be C alpha C2. And if it does, then actually it's also possible to approximate it in this higher regularity space by averages of the modifications of the original field. And so now we can truly extend all the theory of the solution theory developed so far to the case of distributional fields P. So in particular now, if TWB is at least of regularity C alpha C1, I can actually define X to satisfy this equation if and only if it's of the form W plus theta, where theta now solves the Young differential equation. So now this is going to be just convenient notation. This interval is not going to be well defined anymore as a Lebesgue interval, sorry. But now this formulation is still rigorous. And so in particular, if TWB is alpha C2, uniqueness holds in the sense of this definition. And moreover, by the stability property, if we first modify the drift and consider the solution associated to the modified now drift, these solutions will converge as epsilon goes to 0 to the unique solution in the sense of this definition. So this concludes the analytical part of the theory. So we have identified the correct condition to be a regularity condition on TWB, specifically of the form TWB being C alpha C2. Another question is, can we find examples for which this property holds? And the answer is positive. So one way is to see it is the following one. If now we sample W to be a fractional emotional parameter H, and for instance consider B to be an infinity C alpha, alpha being any real parameter, and for simplicity take B to be compactly supported in space uniformly in time, then it can be shown that TWB now is going to be of order C1 C alpha plus 1 over 2H. So here there is the non-trivial trade-off between space and time regularity. We have a regularity boost of order 1 over 2H with respect to the region B, which come with a loss of time regularity from 1 to be only 1/2. And okay, at this point, since H is allowed to be between 0 and 1, we can always, for any given fixed alpha, possibly negative, find H small enough such that alpha plus 1 over 2h is greater than 2, to which we can apply the previous theory. So in particular, it's always possible to find for any distributional field in this kind of class, suitable perturbations which regularize the ODE. And actually, the fractional Brownian motion is just one example of a larger class of Gaussian processes for which this type of regularity holds, which is given by Gaussian processes satisfying a strong local form of non-determinism in the following kind. So instead, if we actually try to pass to the second part of the problem, so point B, so now establishing what we can say for generic continuous additive perturbations, we need a suitable notion of genericity. And the proper notion is given by prevalence, which was first introduced by Christensen and then by Hans Hauen and York. It's a sort of an extension of the concept of full Lebesgue measure sets to the case of infinite dimensional spaces in which the Lebesgue measure does not exist anymore. And the nice feature of this notion of genericity compared, for instance, to bare category type ones is that it allows for probabilistic arguments in the proof. So in particular with Massiliano, what we established is that similarly to the previous case, if we consider B to be an infinity C alpha again, and now delta to be between 0 and 1, then we can establish the regularization for the field TWB for generic delta order continuous functions W, in the sense of, for almost every here means for generic W in the sense of prevalence. And so in particular, again, if we fix alpha possibly negative, we can always find parameter delta small enough such that the generic delta order continuous functions W, will, perturbations W, will make meaningful and actually regularize the ODE in such a way that solutions exist and they are unique. And this is truly what I mean by noiseless here. The point is that this notion of genericity is detached from any reference measure. So truly what we establish is that continuous additive perturbations will regularize the equation without imposing any statistical assumption on the perturbation themselves. So this concludes my presentation, and here is a quick list of the main references. Thank you.